on my hand, and I am going to share my screen. Please let me know if you can see the here. So can everybody see the presentation mode of the slides? One say yes or no?
We can see.
Thank you very much. So as I said, I'm going to talk, give a general overview of generative models. So I'll talk what people usually talk about when they talk about generative models, because surprisingly, if not, there's not so much consensus. And I'm going to give different examples of generative models from different fields. And in the end, we are going to present a couple of hands-on tutorials like code on how to train generative models and to get some results from it. So as I said, I will start with an overview of generative models, what I'll mean in this slide. And this is like something that most people mean when they talk about generative models. I'll make this distinction, which is not a real distinction, but more educational purposes, between probabilistic generative models, which were the generative models that that people were talking before deep learning came into place. And then I'm going to give some examples for deep generative models. In particular, I will talk about the variational autoencoder and the generative adversarial networks that are usually called GANs. Now, for deep generative models, I don't claim that these are the only two families of models that exist. In particular, I'm not going to, I will omit for brevity, and also because there is not much space, and for others I'm going to describe some important families, at least to me. In particular, I'm not going to talk about some models that existed in academia and research, have been popular and very interested to examine, like the restricted Bayesian machines or the deep belief networks, but they haven't found a way in the mainstream applications. I'm also not going to touch about normalizing flows, which is kind of interesting, probabilistic generative model, probabilistic deep, a real probabilistic deep generative model, because it's still in its infancy as far as applications are exist, and variational autoencoders and GANs, at least at the application, have been beating it consistently. So that it hasn't actually produced a breakthrough though yet, although I think there is potential there. And also, I'm not going to describe what are called the autoregressive models, which are examples of these are powerful text generation models like BERT, well, actually GPT-3, which is an autoregressive model. And the reason for this is because they are more specific field models. For example, they assume that your data is a sequence, they have a sequence. So I'm going to just stay in the in models that they don't make this explicit assumption. Some implicit assumptions they do make, the medias will see they work better for some data, less well for others. Okay, and as I said, we'll finish with a hands-on naive example of generative models. The one I'm going to use is naive Bayes. By then, we'll know what is a naive Bayes and a simple GAN example. Okay. So what's generative models? A model. Here, a model is a mathematical function, usually a statistical function, and a generative model is a model that can produce new data instances, and the data here is our input, our axis. Okay. More formally, when we talk about generative model, we assume a model that given an input variable and a target variable, so that means X is our input, and Y is our target, the one that we are trying to predict or to find information about. A probabilistic generative model is a statistical model of the joint probability distribution of both X and Y. So it actually, you create a probability distribution of X and Y, the joint probability distribution. And how does that, this distribution actually enables you to generate models from both X's and Y's. Okay. Now, here I'll make a disclaimer that the term generative model has recently been used for models that generate instances of variables in a way that has no clear relationship between the probability distribution over no relation to the probability distribution of the potential samples and input variables. That means that implicitly there still exists a probability distribution, but we don't know it, or it might be very intractable or very complicated. And an example of these models is the generative adversarial networks that they produce data, that means X and Y's, without implicitly defining this probability distribution ever. Okay. So, okay, so generative models versus what? Like, are there some other kind of modeling? Yes, this is what we call the discriminative models. And these are the models I've been discussing so far. A discriminative model is a model that we all know that we get some input data. This is given, our input is given. This can be numbers, text, images, and is given. We take it through the model, and the model makes some prediction. For example, if the model is a classification model, it will make a classification prediction, whether the input belongs to this class or these classes. In the other hand, that's the discriminative model. We've seen everything. Like, for example, when we talk about image classification using convolutional neural networks, that's a discriminative model where the input is the images, the model is the convolutional neural network supported model, and the output is the class of the image. Okay. Now, in the generative model, things work almost in the other way. Like the model, you have a model, and this model, a model is, as we said, a mathematical function or a statistical function, can generate an example. In reality, because a function is not an active thing, what is usually happening is what I have in the right part of the slide, where the model is triggered or is invoked using some input. Usually that input is random, and we give this input to the model, and the model can generate an example for the data class or the data that the model has been trained on. Okay. So popular probabilistic generative models, and popular here is that you will see a lot in other applications or in textbooks. One is the naive Bayes, and we'll see what is this and why this is a generative model. A Gaussian mixture model, see example of this, hidden Markov model, latent set allocation. For all of them, we see examples of the next slides. Markov random fields, which is a generative model that we talked a lot in the last two tutorials, and the variational autoencoder, which we're going to talk as part of the deep generative models, which is indeed a probabilistic deep generative model. Okay, so we'll start with the naive Bayes. Here we're going to use some of the notation that we see in the previous tutorials, mainly the notations for the directed graphical models, where I'll give a summary. We use a graph in order to define all the variables in the model, as well as their dependencies between them. So if there is a node is a variable, and an edge defines a dependency. Then if a node points to another node, then the second node depends on the first node. So in this case, in the naive Bayes, we have X, which is naive Bayes is a classifier. That means that you give some input, and it produces a number or a value that says what's the class of the input. Okay. And that's what we are going to show. We're not going to assume multi-classification. So it's the simple one. So for example, I have, news articles, and the input is the news articles, and the output of the model is this article is about sports, this article is about politics, this article is about culture, and so on and so forth. So in this model, the Y is the class, what we produce. And the axis is any input that we give to the model. So in our case, the example that I gave is documents, or it could be words of the documents, depending how we defined our what is the input. That depends on the model there. Now, the generative model is that given the label, the naive Bayes can generate the features, the input for that, and in the joint probability distribution, we said that the probabilistic generative model is a joint probability distribution. Here is very simple. That comes from the main assumption that the naive Bayes does, is that given the class, which in our case is the X, all the input, all the features, or the in our case is the Y, all the inputs, all the features, or the X's are independent of each other, in which that means that we can write the probability distribution as simple as a multiplication of the probability of Y, and then the conditional probabilities of every X given Y. And that conditional depends only on one X variable, because as we said, all the others are independent given the Y. And that's how we write that's how we define the probability distribution of the naive Bayes. Now, in practice, these probabilities, we compute these probabilities, and we'll see in the example empirically, like we count in a frequently support, we count how many times we've seen the probability, the classes of each class. So that would be the probability of X's, and the probability of every X value. So if we have two values, it's going to, for X, it's going to be, we're going to compute how many times we've seen the one value of X and how many times we've seen the other value of X, and we'll compute the probability distribution of that. Same thing for the conditional probabilities for all the values of the other input, all the X variables. Okay. Any questions on the naive Bayes? It's pretty simple. It's basically what we do when we compute probabilities in a probability 1-1 class, probably. Okay. Now, another model is pretty popular, is what is called the Gaussian mixture model. Here, we assume that the data, they are produced by a number of Gaussian distributions, and there is also a variable, here I have it as Z, that chooses for its data, for its data point, which Gaussian to use. And this is the Z. Now, graphically, I have it in a vector format. Well, the Z is a vector. That means, so if we have, for example, 4 Gaussians, it's going to be a vector of 4 cells. Each cell has the probability distribution, the probability of, of choosing one Gaussian. And the X node that I have there is basically, it's actually 4 different nodes, each one for each one Gaussian. So the generative model here is that first I produce Z, the vector Z, using some probability distribution, multinomial, for example, because we talked about probability vectors. And from that, I sample that probability distribution to find which Gaussian to use. So if I have 4, it will give me one of 4 numbers, 1, 2, 3, or 4. And then based on which Gaussian the model gives me, I go to that particular Gaussian which has nu and sigma that are computed as part of the model training, and I sample the X using the Gaussian, this particular Gaussian. That means the Gaussian with this particular M and X, mu and sigma. Okay, that is a mean and standard deviation. Okay. So this is a cluster. This is a kind of, I would say, popular clustered model where we assume that each cluster comes from Gaussian distribution, like each Gaussian describes each cluster. So if, for example, we're trying to cluster and we want to create a cluster model with 4 clusters, each one will be defined as a Gaussian distribution. And we have a latent variable, this z variable, which for every point chooses which Gaussian for every point which Gaussian to give it, to assign it to. Okay. Any questions on the Gaussian mixture model? Okay. Another example is an example of a sequence model here, where so far we haven't seen any sequence models like the one variable to depend on the other variable. And one example of this is the hidden Markov model, where again, the axis, which is our input, the axis depend, and when we say input, the input depends on the problem at hand. So for example, if I have a time series problem, the axes are going to be the values of a time series at each particular time stamp. Okay, and the model says that each x is produced by a y, and this is a y is a variable that defines, it's a latent variable that defines something discrete. For example, it could be if I'm having a series of temperatures, for example, the latent variable, it could be whether which day of which hour of the day it is. Okay, it could be, or it could be what are the climate conditions at that particular day that we do not necessarily can't observe. So the Markov hidden model says that there is a dependency, a sequence dependency between these axes, which follows, which agrees with the Markov with the Markov condition, which says that the value of say xn given the value of xn given xn minus 1, so that means the previous neighbor, the direct descendant. Knowing that, we don't need to know the values of any other more previous variables. So we don't need to know the values of a y1 or y2 when we know the value of yn minus 1 in order to compute the values of yn minus 2, n. Okay, and so having said that, that actually defines the joint probability, which is for every the joint probability of the model, which is all the the joint probability of all the x's and all the y's. And as we said, every y only depends on its related x. So x1 only depends on y1, and every y only depends on its previous y. Okay, except from the first one, which doesn't depend, there is no previous for it. So y1 doesn't depend. So we have to create a probability distribution from y1. Okay, and that's how we define the probability distribution of the hidden Markov model. Any questions on the hidden Markov model? And as you see, once we have the joint probability distribution, for each one, this probability tells us exactly how to produce both x's and y's, because we sample from that. We can sample from that probability distribution and get a value, or the values for the ones that we need. Okay. Now, another example that I want to touch upon is what is called the LDA, latent descent allocation, which is an admixture model. Admixture means that well, let me actually describe what is the model, and then I'll describe what is the admixture. So the LDA, or other words called topic modeling. It is a model that has been introduced in the document field, but you can use it in other ones, mapping documents, words and documents to your entities. And so this model says that every document is a probability distribution. That means may contain different topics, and every word in the document comes from a particular topics. So, for example, if I have a news article, a news document, it can contain topics about sports, and it could be also sports like related to football, related to the condition of athletes, as well as other sets of topics. For example, talk about the same document talking about sports news, for example. As I said, talk about athletes, condition of athletes, condition, your own conditions. So those are different topics that you can find on the same document, and every word can be comes from one of those topics. Okay, that mixture of this comes that here the participation of topics in the document is not strict. That means one document can have multiple topics. Okay, well, before usually a document is a single topic, and that's that mixture comes. Okay, so this model has been introduced in order to find latent topics within the documents. As I said, a document about sports can describe different things. For example, it can talk about football, can talk about athletes, it can talk about basketball, and so on and so forth, depending on what the model will find about the topics that exist there. Now, how is this generative model? How this generative model is defined? So, as I said, the model assumes that the input is your words in the document, and every document can come from different, contains different topics, and as I said, a word is generated by one of those topics. So the generative model, how it works there is that first we define the probability distribution for every document. We define the probability distribution of topics within the document. And also for every topic, we define the probability distribution of over words. Here, the topic is defined as a probability distribution of words. So, for example, a topic that talks about basketball, it probably has large probability distribution of words like referee, NBA, while smaller probability values or things like dancing or politics. Okay, so and that's what basically does is for the probability. The model defines first all the topics given a number of topics. This is given to on the from the model. It defines probability distribution of words over each topic, and this is the top part of the schema here. So what it says here is given some parameter, I define a case the number of topics that I want to define. I define for every topic, I create a probability distribution of all the words. And then for every document, and the document here is the rectangle with M. That means that I have M number of documents. The first thing I'm going to do is for every document, I find what kind of topics exist there. So I sample the topics based on the probability distribution of topics within the documents that we'll learn. And then for every word in the document, I sample first to see which topic this word came from. And then for every from this topic, I sample to see which word, which is the word that is produced. That's the generative model. Okay. And one thing I want to note here is that the graph that I have here is kind of a compact and folded graph of the examples that we saw in previous tutorials. So basically, the directed graphical models where variables of the same say family. For example, when I talk about all the topics, the phi, for example, here are only grouped in one circle as opposed to having one node for every variable. So, for example, in the unfolded form, we would have k circles because we have k topics, while here we fold them into one, and this form is usually called the plate notation. Okay. Any example on the, so here you see how the generative model, starting from the topics and the document, we can generate the words. Okay. Any questions on this before we continue on the deep learning, generative models? No. Okay. So, and now I'll give these examples of the two quite important. It means that they have found a lot of applications, mainstream applications of deep generative models. And I'll start with the variational autoencoder because it is a probabilistic, it's a pure probabilistic model, similar to the ones that we've seen. And then we'll go to the GANs. So the variational autoencoder is an unsupervised technique, and consists of two networks, the encoder and the decoder. Now, the generative model is actually only the decoder part. So the decoder taking some random input, giving it some random vector. After it has been trained, it learns to create another vector, which is an instance of the family that the variational encoder has been trained to produce. Now, while training, it learns a latent encoded vector, which is the random input that we have to produce to give when we when we use it to generate some data. And what it learns there, it gets enough information to be able to reconstruct the input. That means it gets enough information, hopefully in a generalized format, that it can reproduce instances of the very similar to the input. And as we'll see, with constraints to come from a multi-dimensional Gaussian distribution, and this is practical, so that when we use it as generative, we can use it in a practical way. And I'll show what we mean by practical case. The latent space is carefully regularized so that random points in that space can generate meaningful data points. Again, I'll give an example of what I mean there. Now, how is the training of the variational autoencoder? An input point is encoded as a distribution over a latent space. As we said, the latent space, this Z, is a space that has enough information to be able to describe instances of the training data set. That means, so when we use it as input to in order to generate something, it can generate meaningful instances of the same family as the one from the training data. A point from that latent space is sampled from that distribution. The reason is because the encoder learns a distribution, but what we actually need as input is a point, because that's what will be given. So we sample a point from that latent distribution. The sample point is then decoded so that it reproduces with aim to reproduce the original input, and the model error is computed, and the error is backpropagated through the network as usual in any deep learning model. Okay, so I haven't touched how this encoder and encoder networks look on purpose, because it doesn't really matter. It's part of the architecture of the particular point, the architecture that somebody will create for a particular point distance. That means that the variational autoencoder does not impose any particular architecture. It can be any neural network architecture. As we said during training, I start with an X, which is a training example of the data that I want to be able, of the family that I want to be able to reproduce. The encoder network, it learns the parameters of a probability distribution. We sample from that probability distribution, and this is so the space, the latent space is both is really described by the probability distribution that we learn. So that means the parameters of that probability distribution that we learn. But then we use that probability distribution to sample in order to be able to get a particular instance, because neural networks do not work with distributions. They work with instances, with values, with vectors, with tensors. We sample from that. And then we use the decoder in order to create another vector, and the train needs to be able to, for that vector to be as close as possible to the original X. So, and this is shown in the loss function. So the first part of the loss function, as we say, is the distance between the vector that is length, the X hat, as well, and the original X. And also, as we said, we add one more part of their error loss, which tries to constrain how this latent distributions that we learn, this encode, the distribution that the encoder learns behaves. Okay, and this is what I call the regularization term. Like, we try to make this probability distribution to have some nice properties, and the nice properties is that the space that this probability distribution creates is continuous, and also that if there are different classes within the family that we learn, that we try to get the classes together. I'll give an example. So if we didn't use, so for this one, it is an example in a particular problem where we want to learn images of numbers, and we have simple images of numbers from 1 to 9. Okay. Now, as we said, if we do not use this second part, this regularization part, which says that, that constraints the distribution to have specific behaviors, the neural network is not constrained and can learn any form. So for this particular problem, what it learns is the one that we see on the left. And we see that nicely it learns to locate, to put classes, points of the same class together. For example, the yellow is the 1 and the purple is the 7. However, it is discontinuous, like there are places in the space that they don't have any point. So why this creates a problem? As we said, in order to use as a generator, we take the decoder. The first thing we do is that we produce a random number, a random vector, and we use that random vector in order to produce something. So if this random vector that we produce it is within the space, that there are no colors, that then the variational autoencoder will create garbage. So that's why this is a bad thing. So we want the space to be as continuous as possible. Okay. And the other thing is that if we only put this regularization, we get an example so at the center, where the space is pretty continuous, but then the classes, the points or the classes are not divided between each other. Like I get one point, and the next one can belong to a completely different class, or all my neighbors belong to completely different classes, which is not what we want. So with a combination, it actually creates a space where it has both these properties, that classes that thinks that they are together create classes create instances of the same class, and as well as for the space is continuous, so that if we create a random vector and we give it as input to the variational autoencoder, chances is that it will be able to create a meaningful vector of the family of points that it learned to, that it was trained on. Okay.
Excuse me, one question.
Yes.
So the regularization term is the same irrespective of the learning task, the data set.
Yes, so yes, this is a good question. It is. And the original, because what you want is that to say that these points are somehow to create something that says these points are close together, and also that they are separated. So the original paper, it said that the probability distribution that is created has to be as close as possible to a Gaussian with mean 0, and what is called the sigma
standard deviation.
Yes, and that found because it is first of all the standard deviation is small, it creates the continuity in the space, and because most of them they try to be close to their mean is close to 0, they how's it called, they create again they don't create this discontinuity. So it is independent, and it comes to the ingenuity of the how to say, of the variational autoencoder creators. Now I think there have been some successful efforts to use other distributions. But the idea there is more like how I'm going to create this, what kind of the soft constraints to put so that the space is continuous, and points that they are close together, they belong to the same class. So that's the constraint that you want to create. So it's pretty general.
Okay, thank you.
Now, you could also put the hard constraints, but then what you need to do is you, how do you say, you have to be able to train it. So the constraint that you create, has, in the case of neural network, has to be differentiable, because that's how you can produce the back propagation. Like, for example, you couldn't use hard constraints that would impose that, because then you wouldn't be able to train a neural network. Okay. So before finishing on the variational autoencoders, I want to just give how what is the probabilistic view of this variational autoencoder. So I think once the variational autoencoder is trained, I think it's pretty straightforward why it's a generative model, because we're using a random input that we produce using some probability distribution. We feed the decoder, and the decoder produces an instance of which is similar to the training data that the variational autoencoder was trained on. Now, this random variable has a prior distribution. That means that whenever you want to produce this vector, and this comes from a standard normal distribution. So you use a standard normal on the dimensionality that your latent vector has been trained. You produce a vector and you feed it to the decoder, and the decoder produces an instance. Okay. Now, the inference is that's where the encoder comes in. Encoder comes in order to train the model, and the model is trained using what's called this amortized variational inference. So what does this mean? Like before we talked about variational inference, that if we have a very complicated distribution, we want to be able to perform inference on this to train it. What we can do is that we can find a simpler distribution, and we learn it, and we train that distribution so that it's as close as possible to the original distribution. Now, using the amortized variational inference, we can actually use the neural network in order to do that. So the amortized variational inference is variation of the variational inference, where instead of optimizing a set of free parameters, we can introduce a parameterized function that maps from the observation space, our inputs, to the parameter space of the approximate posterior. The approximate posterior is the variational distribution that we want to learn. And having that, we can introduce a neural network that accepts an observation as input, and as output, it gives you, it produces this approximate posterior distribution, mainly the parameters that describe this approximate posterior distribution, and that's where the neural network comes. So the neural network is this parameterized function that maps from the observation space to the approximate probability to the approximate posterior distribution, which is our variational probability distribution. Okay, so instead of actually having a inference function that uses all the inputs, we basically learn this neural network, which is this parameterized function that does this mapping. Okay. And this parameterized function is the encoder. And that's why sometimes you can see that they say the encoder is the variational distribution, but it's not really the variational distribution. It's really this mapping from the observation space to the variational distribution. Okay. And this is what I just said graphically. I don't think yes. So as we said, the left part, which is the downwards phase, is the generative phase. Is that we first, given an input, which is, as we said, we randomly produce it by sampling from a normal. We produce this latent space, latent vector, and we use the decoder in order to produce a value, a vector, an instance that is similar to what the variational autoencoder has learned to produce. And the training is shown in the the right part, where, as we said, this encoder is creating this is representing this mapping of the observation space, which is our training data, to the latent space, and the latent space here is described by the parameters of the probability distribution that we learn. That's why we said that the decoder actually produces a mean and a standard deviation. Okay. And any other questions? Max, I'm not going to. Not here. Before going to the applications, we'll see some examples of how variational autoencoders have been used. So variational autoencoders had although they had been respected as an idea from the beginning, it kind of had a hard time keeping up with the GANs that we're going to see next in applications where both of them were used. Mainly, at first they were used for image generation, and variational encoders tended to create more blurry images, like the examples I have here. And so for some years, they thought that they were inherently less powerful. Recently, they have actually have some breakthroughs where this has been reversed, and the consensus is probably the reason that we did not get good results is because we did not know how to use them correctly, or they were harder to understand because it was a probabilistic model. So, so there is a surge of interest in variational encoders, and have been used to as powerful to generate different data sets, for example, images, music, language modeling, neuroimaging brain mapping. As we'll see, in both autoencoders and the GANs, they have been very successful in what we call continuous data, like images, video, music, signals. And they have been surpassed by other models in more data that are more discretized, like for example text. So although I have language model in here, text generation, different models, namely the autoregressive that we have discussed, that we have referred to in the beginning, have given better results. So an example of oh, I didn't know, these actually have been, I don't know if you could hear it. It has been created by generative autoencoders. Okay, so now we'll go to the last part, which is the GANs, the generative adversarial networks. As I said, although GANs, let me explain. So although GANs are not a probabilistic model per se, because we don't have a probability distribution, at least not an explicit one, we can give it some the probabilistic motivation of this. So that's what this slide comes. So complex data are generated by very complex probability distribution of very large spaces. A variational autoencoder was actually producing things in a normal distribution in a very, very large space. Again, but it could be the case that the data are so complex that Gaussians or a mixture of Gaussians on any other family of these distributions, they cannot describe it they're not representative one. So this distribution exists, but most of the times we don't know how it looks, or we don't have a way to do anything with this, mainly to sample from this distribution, because as we saw, how we use these distributions in order to produce data, we sample from those distributions. With GANs, we express such distribution as a very complex transformation of normal variables. So with GANs, we use as input something that comes from a normal variable, and then we pass it through the GAN, which is a neural network, and this network has learned to transform this variable, which is initially normal, to a variable in the probability distribution of the data, which we don't know, but we learn how to transform there. To map. Okay, so that's basically the graphical example of here. So with how we can think of the generative process using GANs is that we use some probability distribution and normal in order to get an input random variable and input vector, random vector. And this could be uniform, but as we said, usually they use normal distributions. We pass it through this generative model, this GAN, and this GAN during training has learned how to transform the vector, the original vector, to another vector in the probability distribution, the actual probability or the approximation of the probability distribution of the data. And once we have this vector is actually a valid instance of a data point in the data set that we want to generate from. So for example, here, assume that we have images of simple images of, say, creatures. We say, in order to create a new creature, after we have learned the GAN, we sample from a normal distribution or a uniform, some simple distribution. We pass it through the GAN gives us a new vector, and once we transform it into, we reshape it into an image that gives us a valid image of this creature. Okay. And the GAN comes from, the name comes from that the adversarial train is used in order to train this neural network to learn this complex transformation function. So, as I said, this is just a motivation. It's not, it has not been proven or anything. That's basically how one can think about it. So, GANs is an unsupervised modeling technique that learns the regularities or patterns in input data in such a way that the model can be used to generate or output new examples that could have been drawn from the original data set, from the family, as we said, of the original data set. The problem is framed as a supervised learning problem. The trained data comes from the examples of the original data set that we want to sample from. So if we want to sample images of people, specific images of people, our original data set, our trained data set comes from examples of the people that we want to learn how to generate. So the model has two submodels, a generator model that generates new examples. So once we train it, this is a part of the model that will be used in order to generate new examples, and a discriminator model that tries to classify examples as either real or generated. So what happens is we feed to the discriminator model examples that may come either from the original data set or from data set that come from the generator model, because the generator, as we said, learns to generate some examples, and the discriminator tries to learn whether the examples that it shows comes from the real data set, the original data set, or it is fake data set coming from the generator. And the two models are trained together in a zero-sum adversarial game until the discriminator model is fooled about, well, half the time is fooled as less as possible, meaning that the generator actually is fooled enough so that the generator is generating plausible examples. Okay, so we don't want it to be the discriminator very strong, because that means that the generator is not generating good examples. But we want to also not be completely weak, because that means that the discriminator is not a good classification model. So even if the generator does not produce good examples, still can say that it is the discriminator is still can it does not learn that. So it is a red rate for the discriminator. That's why in practice, or we say about half the time, it is we try to actually find a good value for this trade-off. Okay. Now, as we said, the generator model is it takes a fixed length random vector. This is the vector that after in the generation part will be used as input. This, as we said, this usually comes from a Gaussian distribution, but as I said, it could be any simple distribution. Gaussian is usually, so, but it's usually drawn from a Gaussian distribution. This vector is used to seed the generate process, and after training, it has learned to produce a multidimensional vector that corresponds to valid points of the original data set. Now here I say forming a compressed representation. That means, for example, that it might not produce the actual a data point might not produce an actual image, but it produces something, a vector that can be easily, that is a compressed representation, so representation of an image. So from that vector, we can easily produce in with some simple transformation, an example of the original data set, similar to the original data set. Okay. We don't want the generator to learn to produce only, for example, in the original data set, because then it has not learned. Okay. Now, as we said, the discriminator models, it takes an input example, and the input example can come from both the original dataset, the training dataset, as well as from the points that have been generated by the generator, and it learns to discriminate whether the input example comes from it is a real it's a real point from the original dataset, or it came from the generator. Okay, so. Here, I think this is again a graphical representation of the process that we just described. The interesting thing here is that the generator, and we'll see that in the next slides, it learns to generate the data from the input distribution without explicitly having something in the training process, in the loss function, that compares the two distributions. That's the kind of an ingenuity that's of these GANs. It only learns by using this adversarial loss. We'll just see. Okay. And the loss function, what I'm going to say here, the original loss function, the simple form that appeared in the original GAN paper. It is the same for both generator and discriminator. Usually in practice, how we train this model is that we train one model for a little while, then we fix this model, and then we learn the parameters of the other model, and we continue this changing between training the discriminator and the generator until we think that the generator has learned to produce good examples. So, but as I said, in both cases, while trained them, it uses the same loss function. The first part of this loss function, it says the only difference is that the generator is trying to minimize this loss function, while the generator is trying to maximize this loss function. So maximizing this loss function, what it does is that the discriminator learns by maximizing it, is learning to predict parts of this original data set as correct. That's the first part, because dx here is the original data set. Actually, this is the estimate that the real data set is real, so the dx, and we take the minimum of this over all the data of the points in the data set. And also it learns to say that a data set that came from the generator are fake. That's the second part. That's why we have 1 minus dgz. That is the estimate, is the prediction of the discriminator saying that a fake instance is real. So if the 1 minus say that the fake instance is fake. So by maximizing that, it tries to maximize both to say that the real data is real and the fake data is fake. Now, by minimizing in the generator, in this case, it uses the same loss function, but it really minimizes the second part because it cannot change the first part. The first part is the prediction on the real data set. So the generator cannot do anything. So it only is affected by the second part. The second part is that by minimizing it, is trying to actually make the generator make more mistakes. So that's the adversarial, the training the game that we see there. Okay. Any questions on this? And as we said here, you see that the generator learns, the loss function has no, the generator does not have any access to the, it does not do any comparison between the distribution that it learns and the original distribution. It only tries to make the discriminator make more mistakes. So that was the, as we said, the original loss that very fast, very quickly has been how to say, ameliorated, because the GANs, although it is a very neat idea, in practice very hard to train. One thing that it can happen there is that the loss can become oscillating. That means that it doesn't, after a while, it does not it does not decrease anymore, but it actually oscillates, in which case the network does not learn anymore. The other thing that happens there is a mode collapse, where the generator is learning to generate only a small data set of very good outcomes, in which case the generalizability of the generator is not good. The other thing, the challenge, is that the loss is quite uninformative, like seeing the loss decreasing up to some point doesn't really, there is no correlation between the value of the loss and how good the model is. So you have just looking at the loss does not give us much information on whether we have trained enough. And another big one is that if the discriminator is very good, like it's very, it can, it has a very good prediction both on the real data set and the fake data set, then the discriminator, the generator cannot keep up with this because of vanishing gradients. That means that it does not learn anymore. So that's a practical problem. And also because of the two models, it has a large number of hyperparameters that have to learn. Okay. So as I said, some of these challenges have been new losses that very fast came up, and now there are actually a large number of losses for GANs that have been appeared in order to be able to tackle these problems, try to mitigate these problems. Okay, some of these problems, for example, the number of hyperparameters cannot be changed by the loss. Now, before continuing, before the last part was actually some variations or applications of GANs. Any questions? Yeah. So GANs have actually been, I think people like them, so they have been used both because they have really good results in specific data sets, namely images. So a large number of applications, generative applications, and variations of GANs have appeared. And the variation of GANs here comes is that each application, it doesn't really use the pure GAN that we described, but actually does creates variations of this, either change the loss function, changes some of the assumptions depending on the architecture also. But the main idea is the adversarial training. So some GAN variations that have been appeared is progressive GANs, where instead of trying to instead of learning the generator, instead of trying to learn the actual image, it's learning something in some part learns a simpler example, like very low resolution images where the subsequent layers are details. So that as I said, is for this particular data set, data family images. So it has been shown that it traces more quickly and produces higher resolution, better quality images. Conditional GANs, that's an interesting variation, is where the model, instead of learning the joint probability distribution, actually learns the conditional probability. In this case, what would this make a difference is that in the unconditional GAN would produce random digits, like we don't know what digit it would produce or what family of images it would produce. So for example, if we have digits, it would produce random images, while conditional on the if we train a conditional GAN, we can actually constrain the GAN to learn images of a specific family. In the case of digits, it could learn specific digits. We could actually use it to generate specific in digits. Okay. Applications of GANs, there are a lot, and I just have some examples here. I don't even claim that these are the most important ones. So image generation has been used a lot, not only in general images, the different domains like medicine and biology. Image-to-image translation, where where we take an image and map it to a generated output image with different properties, for example, different colors. Cycle GAN is a variation, that's where it comes. It's an application with the variations in the original GAN architecture. Cycle GAN transforms images from one set into images that would possibly belong to another dataset. I use it here, for example. Interesting is that you get an image and you produce an image that could come from, it could be a Monet image, say, impressionist image. Super resolution, very important, where you get an image and you increase the resolution of the images that you create, a better quality image. It has been very successful in super resolution. Text-to-image synthesis has been used where you write the text and it produces an image. Now here, that's where different models come in place. As I said, although originally GANs have been used for that and they were very powerful, different models that combine GANs with autoregressive models, which, as I said, they're better for sequence-based data like text, have shown better results. For example, DALI is an example where it still has, it is a combination of a GAN and an autoregressive model. Other examples is face in painting. Text-to-speech, music generation, I have an example here. I have text generation, but as I said, autoregressive models, namely GPT-3, which is OpenAI autoregressive model for text generation, it has surpassed it by straddles, I would say. Other things, video prediction and 3D object generation. It has been applied there. We see the results are not great for 3D objects, but 3D object in general is a very challenging field. So what we get here is probably a good enough result for the state of the art, or I wouldn't say good enough, I would say state of the art result. Okay. So at this point, I'll just stop this concludes the slides, and I would ask you if you have any additional questions. Otherwise, we'll go for the example. I'm just going to stop sharing for a minute. And okay, so I'll start with a simple example of generating data using diiP Base. And oh, actually, let me see something. Just a minute that I have. Yes, I started there. Okay, so okay, can you see the Jupyter notebook or my browser, on my browser?
Yes, we can see.
Thank you. So we saw the diiP Base. The diiP Base is a simple classifier with the generative processes that I learned. I can generate the input, which is the features, and we'll see what we have. I will give you example of features here by first generating a label, and then the label, the features given the label. So I'm going to use the avatars data set, which program. Let me see if you can see. Here, you can actually give some examples, features like I want an avatar, produces avatars that, what is the avatar style? And you can give different values for the features of the avatar. So for example, see what it has here. The top, it can have a hat, long hair fro, and so on and so forth. And difference, what is the eyes, color, eyebrows, mouth, and so on and so forth. Okay, so the features here is all the different values that we see in each one of these. The feature attributes is the attributes that we have, accessories, hair color, facial hair, and the values for each one of them is the ones that we see in the top-down list. Okay, so I'll use some data that already have data of actual avatars. Okay, so I load this data. So here I have an example where the class is, we have 4 classes, is, as far as I remember, is boy, man, woman, and girl. Okay, and this is the class. And for each one of them, we have different attributes: top type, accessory type, hair color, and for each attribute, different values which describe what the value we want in that type. Okay, so to train it, as I said in the slides, one way to train it is empirically, where we learn the probabilities by in a frequency approach by counting how many times something has been has appeared in my data set. So my data set is the ones that I have in the table. So the first thing is that I'm going to create the probability distribution of the class. With the class has 4 different values: man, woman, boy. So I learn a probability for each one of these groups. So I learned that, and if you see the code, is just saying how many times I've seen a man, given all the data set, all the rows that I have in the table. Okay, so we get that. The next one, the code it's not complicated. It does the same thing. So for every feature that we have, we're going to count how many times how this feature appeared given a class. So for each class, we're going to count how many times we've seen top type, accessories type, a particular value of top type, accessories type, and another one. Now, one thing here is what I want to say is that usually we also use what is called a Laplacian smoothing, so that in case in our data, because the frequency approach, we might not have examples of, like, we might not have a mouth round for the boy. We just put a number there that in case I get 0, or my probability is not 0, but it's some small probability. That's the Laplacian smoothing. Okay, and that will give us all these probabilities. So for example, given that it is a boy, the top type having short hair, the scissor side part is 0.05, and so on and so forth. Okay. And then finally, we use these probability distributions to create new avatars. And how we create new avatars? First, we sample from the class. So we use the probabilities of being boy, woman, man, girl, and we get a class for this new avatar. Then it might say man, and then we use this value in order to create the to sample from the to sample the other features given the probability that we already learned. And that's basically what it's doing here. And then one thing is that we can inspect this avatar. So in order to inspect these avatars, we'll click here. One thing is in this URL, it also gives you the features that it has learned. So for example, it learned a circle, avatar style equals circle, and top type is long hair, Frida, and so on and so forth. So let's see the first one. Produce this. Ooh, that doesn't look like a good avatar, but it produced this one. Okay. So that's basically the example of a generating using a simple probabilistic model. And the same thing is with the other models that we saw, except that the probability distributions look different. And the train might be different depending on the probability distributions. And just give me a minute, I'm going to stop sharing because I have to switch some engines in order to run the GAN. Now for the GAN, I'm going to give you an example of a GAN that does a simple thing. It actually learns to produce a sign distribution. Just give me a minute and see. Okay, so I'm sharing again. Just give me a minute. Share screen. Okay, so you can see my browser again, right? Somebody?
Yes, we can.
Okay, so we'll define some things. So we'll generate some training data that produce this cosine. Randomly, I'm just generate some data that create this cosine function, so that the data is the x and y's, and the function that it learns is the cosine function. So first I define a discriminator model. As we saw, I still haven't given any information about what is the architecture of this GAN. I just talked about the loss function. So the architecture is at the discretion of the GAN creator, and which depends on the application. So here is a simple one, so I can use dense layers. So I have a MLPs, multi-layer perceptors. I have three multi-layer perceptors with a dropout in between for regularization. So I run that. And so graphically it looks like this. I have three MLPs. It doesn't show if each MLP has a dropout. Then I have a dense layer that produces this, excuse me, it dense layers and a sigmoid in order to create the non-linearity there. The generator is even simpler. I have only sorry, the sigmoid here you want it for the classification. That was the discriminator. So it gets the dense layer, the previous dense layer, and it puts a score that says whether the input belongs to the class or not. In this case, it's a real or not. Okay. The generator is even simpler. Two MLPs and a dense layer which produces a vector. And the dense layer is a vector 2 because our probability or dimensionality is to x and y. Okay. Visualize it again. Looks like this. Now for the model training, it will take some time to run. What is interesting, as we said, is that we use the same loss function for both of them. So it shows, I don't know if you can see my highlighting here. The loss function for the discriminator is the loss function. It's the same loss function, but it uses all the samples, and all the samples is a concatenation of the real samples, the training data that we have, and the generated samples. And the generator, the loss function is here. We only use the right? Yes, it only uses the excuse me. It only uses, sorry, it only uses the second part of the loss, as we saw, because we only want to see what happens, the results of the discriminator for the generated data. And the way I have it is that first we learn the discriminator. So the generator is fixed. The parameters are fixed, and we learn the discriminator. Then we fix the parameters of the discriminator, and we learn the parameters of the generator. That comes because I have the parameters in different structures, and I say which parameters to change in its time, and I will learn it. It will take some time to learn here. While waiting, you can ask some question. I might not leave it because it does take some time. I don't have a GPU underlined, so it takes some time. But finally, in order to see the generated data that we get the generator model, and we create some generated examples, and they look like this, which is pretty close to the cosine that the training data that we have. And as so far, I'm going to stop sharing, leave it running. And if you have final questions, I'll be happy to answer them. No? Otherwise, thank you very much. I'll stop recording first.